I think we'll like this problem here. They give us a first derivative. Part A wants us to find the second derivative. So we're going to do the derivative of x squared is 2x. The derivative of that is going to be 1/2. Remember, if you do the derivative of y's in it, you got to tag on the y primes or the dy dx. So we'll tag that on right there. And then it mentions in terms of x and y, which means it doesn't want the dy dx right there. We got to substitute what the dy dx is equal to from the initial problem. So boom, there's our second derivative there. Now, part B, it says let there be a particular solution. Notice it doesn't say find the particular solution to the differential equation. There's no way on this one to move the dx over and then separate your variables by doing legal algebra. They're not meaning for us to find the particular solution. Even on letter D, it says let it equal. It doesn't say find it. It has us doing other things there. So just because you see that doesn't mean you're going to find those. But this one just mentions, does the graph have a relative max, relative min, or neither at this particular point? Now, they will red flag this from a mile away. Anytime they have you find the second derivative and then turn right around and immediately ask us, hey, does something have a max, min, or neither? They're meaning for us to use that second derivative test from your blue packets there, okay? So here's what I'm gonna do. To find a max or min at this point, -2/8, all I'm gonna do, first I'm gonna plug it into that first derivative, see if that first derivative is equal to 0. So when I plug the -2/8 in for this, for x and the y, I did get 4 minus 4, I did get 0. Now, if I don't get 0 for that first derivative, then it's neither, all right? That's the first thing, is your first derivative must be equal to 0 for it to be a max or min. Now, just because it's equal to 0 doesn't mean it's gonna be a max or min. We just gotta check it now, all right? Now, here's what we're gonna use. Since we have the second derivative, I'm gonna use the second derivative test. So I'm now gonna take the point -2/8, plug it in place for x and y into the second derivative that we found right there. And then so that's going to give us a -4. And then remember what your second derivative test tells us. This is not the first time we've seen that. That is our double D on our blue sheet here. If our first derivative is equal to 0 and our second derivative is also positive, that means our graph levels off and it's concave up, forcing it to be a relative min. If the first derivative is 0 and the second derivative is negative, that means the graph is concave down, forcing that to be a max. And so since my first derivative is 0, second derivative is negative, that means the graph levels off and is concave down at the same time. That makes that a relative max right there. So you just got to mention f has a relative max at that point. Since f prime is 0, f double prime is negative. Those two items is what makes that thing a maximum and not a minimum or nothing at all. You don't have to call it the second derivative test, but that's what it is that we're doing right there. If I would have gotten a positive answer, that would have been a concave up, then it would have been a relative min. If I get the derivative is equal to 0, that means it's neither right away. I might just double check that real quick, but it's not going to be neither if that y prime is not equal to 0 there. All right, now letter C has some limits involved. And they've been kind of throwing like this L'Hopital's rule ass lately there, okay? So you're supposed to evaluate this limit, and it tells us g of -1 is equal to 2. So when I do limit as x approaches -1, we're going to plug in the -1 for the x's. So that's going to give us 0 on the bottom. And also when I plug in g of -1, that's equal to 2. So I get 2 minus 2, which is also 0 on the top. Now don't write equals 0 over 0. Just put that off to the side a little bit. They don't like when you say it's equal 0, 0. The limit is equal to 0 over 0, but the function, you know, they're a little picky about those things sometimes, okay? But so that just means I can use L'Hopital's rule. So I did the derivative of the top, did the derivative of the bottom, and now I'm going to plug in the -1. So g prime of -1, okay? That g prime, that's a derivative. The only first derivative that we have in this whole problem is this right here. So it might be a little bit weird, but that's the only thing that you can use right there. So you're going to go to that, and you're going to plug in the -1 for the x. And when the x is -1, the y value is 2. So I'm taking this point -1, 2, plugging it into that dy dx notation. And when I got plugged in -1 on the bottom, I did get 0. And when I plugged that point into that first derivative, I did also get 0. So it was still in that indeterminate form, 0 over 0. So let's do L'Hopital's rule again. So I did the derivative of that was g double prime, and this is just 6x plus 6. So the derivative of that is just going to be a nice number of 6. And now when I plug in -1, I get g double prime of -1. So since I have a 6 on the bottom, I know it's not going to be indeterminate form anymore. It can't be 0 over 0. And so to the second derivative, that's where I'm going to take this point -1, 2, plug that in for the x and y into that first derivative. Or you can even go back here. We know the first derivative right there was 0. So you're going to go like, hey, there's -2 minus 1/2 times 0, or just plug it into the whole thing here. But the bottom line is you're taking that point, plugging into the second derivative. that you found in part A. And then I got -2 for that. So -1/3 is our answer for letter C there. So when you start working with limits, you know, a lot of times they're meaning for us to probably use L'Hopital's rule at some point in that problem there. But and then if you have 0 over 0 or infinity over infinity, just kind of write those things off to the side. They don't like when you put equal 0 over 0, the limit is equal to that, or, you know, so just be a little bit careful with that and bring down that limit notation and do your derivatives right there. All right, and then letter D is your Euler's method, okay? So we know how to do this, but you just gotta practice this without the calculator. It tells us 2 equal steps to go from h of 0 to h of 1. So I'm gonna go 0, 1/2, 1. There's my 2 equal steps, which means delta x is gonna be 1/2. And then they tell us the starting point is 0, 2. So you're gonna take both of those numbers, plug them in for x and y. It says delta x, which is the 1/2, and I'm gonna take the 0 and the 2, plug it into the x and y to that first derivative, and that's where I'm getting to that -1. And then you're gonna take 2 plus a -1/2 to get the 3/2 right there. And then that's your new starting point. And now the delta x is still the 1/2 that we talked about. And then you're gonna take a 1/2, 3/2, plug it into that first derivative for the x and the y, get a -1/4 for that, and then 3/2 minus -1/4. Kind of see my arithmetic, my scratch work at the bottom right there. I was real careful how I did that, and then I was real careful how I did that, got my common denominators, and then just did basic arithmetic there, got the 5/4. That's our final answer right there. Colored pens, colored pencils, markers.